I'm going to look at practice question set number 2B that we had assigned over the weekend here, starting with question number 1. We have a situation here in the stem of the question, or in the information box, I should say, that talks about skiing. We're in the starting box, okay? Presumably in the starting box before we actually start, we're not moving, right? The skier is just standing there. And then as the skier leaves the starting box or the starting gate, he's moving at 1.6 meters per second. Then he goes down the hill, 80 meters, 20 meters per second. A little bit later on, 33 meters per second. Got a mass of 68.2 kilograms here. In this question where it says the magnitude of the impulse on the skier as he leaves the starting gate, I think it's relatively clear that we're referring to just this. We don't care what happens after the skier goes down the hill or during the time the skier is going down the hill. We only care what happens as the skier is in the starting gate. So this first paragraph is all that's relevant here. Now, you could see a situation like this where there's maybe 2 or 3 or 4 questions that go with the box of information, and something does relate to the information in the second paragraph. Sometimes it does, sometimes it doesn't. In this case, it just doesn't. Now, let's write down a few givens for question number 1 here. Clearly, we're asked to find impulse. We're going to use impulse, this thing that we've been doing over the last few days, to solve this question. But what givens do we have? We want to be led to one of the 2 impulse equations, right? The givens are going to tell us which one of the 2. I'll give you the first one. This is the easy one. 68.2 kilograms. What else we got? What else we got? That's relevant, that is. Yep. What's VF? 1.60 meters per second. But doesn't that say the skier leaves the starting gate with an initial speed of 1.6 meters per second? It does say that. But yet you told me it's VF? What is it? Is it VI or is it VF? It is VF. It tells me an initial speed, but you got to be careful with terms like that, right? That would be VI, the initial speed, if you're analyzing the trip down the hill. But we're not. We're analyzing the starting gate itself. So the initial velocity for the trip down the hill, which is what they provide for us there, is the same as the final velocity for the starting gate, right? Looks like you guys managed to figure that out. What's VI going to be? 0 meters per second. Yeah, presumably the skier is starting at rest in the starting gate. Now, looks like M, VI, VF, looks like we're going to use this, right? Delta P is equal to M times delta V. We get 68.2 kilograms times delta V, not V, but delta V. Now in this case, because VI is 0, you would get away with it if you forgot to include both velocities, but that's not always going to happen. So we want to get in the habit of using delta V and subtracting so that sometime when VI isn't 0, we're not going to get messed up by that. The answer to that, when I do the math, works out to be 1.09 times 10 to the 2. The units that they give us are Newton seconds, but they could also have been given as not Newton seconds, but kilograms times meters per second. Good. Either one of those would be fine. All right, number 2. I think number 2 is the one that challenged people the most on this. I know there's several people that had a little bit of an issue with, or a lot of an issue with this question. It's a tough question, actually. This is a tough question. It says a full draw is the maximum distance that an archer can pull back an arrow. Using a recurve bow shown below, a particular archer requires an average force of 130 newtons to pull a full draw of 70 centimeters. I'm just going to circle that because I want to be in meters, right? Draw attention to it. Mass of the arrow is 20.6 grams. Got centimeters all over the place down here, and 20.6 grams. The question says, when the archer releases the arrow from full draw, the magnitude of the impulse the bow gives to the arrow is what? We're looking for the impulse here. Okay, so in terms of figuring out, in essence, what to do, not hard at all. What's the impulse? Well, let's use our impulse equation, right? If we're looking for impulse, you're going to use impulse. But the problem is we have 2 of them. We have impulse is equal to F times delta T, and we have impulse is equal to M times delta V. Now, we're looking for delta P. We have F, and we have m. That's not enough. It's not enough to solve for delta p. We need t, so we can multiply f times t, or we need delta v, so we can multiply m times delta v. So what do? Let's get one of them. Let's get either t or delta v. Now, which one do we get? That's a good question. Which one do we get? It doesn't matter. Which one's easier for you to get? Get the one that's easier for you to get. Some of you probably tried solving for delta t first. That's fine. Some of you probably tried solving for delta v first. That's fine. I'm going to show you both. Solving for t, multiply f times t. Solving for delta v, multiplying m times delta v. They both work. They both give you the same answer. But they have to, right? If they're both valid equations, they both have to give you the same answer. Okay, let's do t first. Let's do t first. Let's start by saying f is equal to m times a. Why? Well, because that's valid. Because I thought of that equation, and it's valid. Let's rearrange it to solve for a. Now, if I start using this, I'm not necessarily sure that it's going to lead me to an answer, right? It's a worst case scenario. It doesn't lead me to anything. It's a wild goose chase, and I come to a dead end, and I have to start again. No big deal. I get 6 hours to write this diploma exam. If you go on a wild goose chase for a minute and a half on this question, oh well, not a big deal. Just start something else. I can solve for acceleration. I don't actually know what it works out to be because I didn't do it this way. This isn't the way that I did it on my answer key. But you can do that, right? A is equal to f over m. You can solve for acceleration. But that's not delta t. How am I going to get delta t from that? Can I? How about this? Why don't I try this? D is equal to VIT plus 1/2 a times t squared. Is that a valid equation? Sure it is. It's accelerating. VI is 0. I'm going to say t here is equal to 2 times d over a. Right? The 2 goes up by multiplying, a goes down by dividing, and then we get a square root. So, oh, look at that. I don't know what that time is, again, because I didn't do it this way. But once you've got that time, you can sub it in there and say f times delta t is whatever. Works out, by the way, to be 1.94 Newton seconds. How many people did it that way? Oh, 1. All right. That's fine. There's other ways of doing it as well. Like, for instance, I could have said f is equal to m times a. Solve for a. Whatever that is. And then I could have said from that, vf squared is equal to vi squared plus 2ad. Got a, got d, got vi is 0, solve for vf. Since vi is 0, I could sub that in there and solve for delta p using that equation, m times delta v, and guess what I'd get? 1/94, of course. How many people did it that way? More. Okay, more. Yeah?
I'm just wondering, it's probably not efficient, but could you technically do it through E equals force kind of systems?
Yes, that's my next way, actually. We call it the work energy theorem. The work energy theorem. So this is absolutely fine. There's no issue with this whatsoever. Now, the question we just had up here was, could we use work, like F times distance, force times displacement? Is there a force? Is there a displacement? Yes, that's valid. So let's try it. I'm going to say work is equal to delta E equals F times D. This is what we call the work energy theorem. If you look back at the board here, back of the room, there's 10 physics principles, 0 through 9. On your data sheet, in the bottom left-hand corner of your data sheet, we see the same 10 physics principles. You will 100% guaranteed get at least one question on your diploma exam that asks you to list the physics principle or physics principles used in answering a particular question. They promise us, they tell teachers that they're going to give us at least one of those questions where we have to identify, in fact, 2 physics principles that you used in answering a question. If you did it the green way or the blue way, the way that we just showed you, the physics principle that you would have identified would have been principle number 1, accelerated motion, right here. F net is not equal to 0, right? It accelerated, right? As long as you use F equals ma or any of those acceleration equations, you've used physics principle number 1. Now, if you were to do it this way, the way that we're about to show you, that wouldn't be physics principle number 1, that would be physics principle number 3, the work-energy theorem. Work is equal to the change in energy. The final energy here would be kinetic, right? We always look at one type of energy here. Kinetic, well, what's the initial kinetic? 0. Final kinetic is 1 F mv squared. The initial kinetic is 0, equal to F times d. We have F, we have d, we have m. We could solve for Vf there. We solve for Vf. Vi is 0, so we've got delta V. We could sub it in here and solve for it, give you 1.94. So exactly the same answer. We've just got 3 different ways of answering this question. The first 2 ways involve principle number 1. The last way involves principle number 3. Does that make sense? We'll, as the semester goes on, we'll refer to those physics principles quite often. Today's the first time that we are. Okay, we'll refer to them quite often as we look at a new concept, and just from time to time look at what principle we used to solve something, just to make you familiar with them, so that when you get that question on your exam, you're going to be familiar with it. How many people got 1.94, by the way, for that? Good. That's good, actually. I'm happy with that. That's a hard question. For that many people to have gotten it correct is a pretty positive thing, I think. All right, last question here, number 2. It says, a rock climber falls and is saved from injuries by a climbing rope that's slightly elastic. The importance of the elasticity of the climbing rope can be understood in terms of impulse, blah, blah, blah. You'll remember last week I told you, you're going to get this question. You're going to get this question on your unit test, and you're almost certainly going to get this question on your diploma exam. It may be phrased as a airbag question. It may be phrased as a cradling a basketball as you catch it question. It may be phrased as a why do you bend your knees when you jump off a desk question. Or it may be phrased as a elastic climbing rope question. Bottom line is, when you see this question that asks you about something that cushions an impact, the answer is always what? Increase stopping time, decrease force. The impulse is predetermined. Increase stopping time, decrease force. The answer is A. If you remember, last week we talked about those 2 situations that can be explained by qualitative impulse. When we have the predetermined impulse and when we have the non-predetermined impulse. The predetermined impulse occurred when we were stopping an object. That's exactly what we have here. We're stopping the climber. The climber falls. The climber has to stop. It's the rope that stops the climber. This cushions the impact when the climber falls. Okay, we're stopping an object. The other one is when we're starting an object, like the golf ball or the baseball or something like that. When we're stopping an object, delta P is unaffected by F or T. Doesn't go up or down, no matter what happens to time or force. Rather, we would say that increase in the time decreases the force. Time and force affect each other. not the impulse. Whereas when we're starting an object down here, time and force do not affect each other. Rather, increasing the force doesn't change the time, it increases the impulse. And similarly, increasing the time doesn't affect the force, rather it increases the impulse. Got it? Was it this class that somebody asked the other day about the flex in the hockey stick? No? I thought it was a good question. It must have been period 4. Somebody was asking about hockey stick flex, and you guys know what I mean, right? When you, my 8-year-old has a, I think it's like a 50 flex. Like it bends like crazy. Like if you put a lot of force on it, I worry like when I push it down that I'll break it, but I don't. It bends like this, like crazy. What's the purpose of that? Like why would you want such a flex in a hockey stick? There's advantages and disadvantages, by the way. It's not all advantage. What's the disadvantage? Yeah, Daniel?
Disadvantage?
Sorry, the advantage, I mean, sorry.
It increases the amount of time the stick is in contact with.
Yeah, if it's bending, it's increasing the amount of time that the puck is in contact with the stick for. That's like flex on a golf club, right? Same type of idea. Increase amount of time. That doesn't decrease the force, rather it increases the impulse. Now the disadvantage to that would be creates kind of a whipping motion, and when you have this whipping motion, it potentially decreases your accuracy. Okay? So the puck goes harder, but not necessarily quite as accurate. For me, when I use a stick with a lot of flex, it doesn't increase the velocity of the puck all that much, but nor does it increase or decrease the accuracy of my already inaccurate shot. Doesn't seem to make any difference any way you look at it, but it's supposed to increase the impulse and potentially decrease your accuracy. Good?